Giving it another minute. Okay, perfect. Let's go ahead and get started. Good morning, everyone. My name is Shannon Hauk. I'm a staff scientist at Q-Chem, and we are very excited today to have Jonathan Fetherolf from Princeton joining us. He initially got his BA at Rutgers University in 2016, doing a double major in chemistry and physics, and then he worked with Timothy Birkelbach at Columbia University for his PhD work. He graduated from there and then moved on to a postdoc at Princeton University with Professor Ham Schiffer, where he's currently working on a lot of nuclear electronic orbital methods, specifically focusing on some low scaling perturbation theory and couple cluster methods for ground and excited states properties of molecules. And he'll be telling us a little bit about his work with development of those methods in Q-Chem today. So we're really excited to have him here. And without any further ado, I will go ahead and actually, one quick logistical thing. If you have any questions throughout the duration of this webinar, we will be answering those at the end of the session, but you can post them in the chat at the bottom. So thank you so much. And without any additional further ado, I'll go ahead and hand this over to Jonathan. Thank you.
All right, let me just share my screen.
Perfect. Thank you.
All right, looks good?
Yes.
Okay, great. Thank you so much, Shannon, for the introduction, and thanks to Q-Chem and Shannon for organizing this and inviting me. So my name is Jonathan Fetherolf. I'm in Sharon Hammer-Schiffer's group. Here, let me give myself a laser pointer. And I'm in the Hammer-Schiffer group at Princeton University, where we kind of focus a lot on nuclear quantum effects. And today I'm going to be talking about nuclear electronic orbital theory, and specifically I'm going to be talking about ab initio wave function methods. So I'm going to start out just with a brief kind of overview of what is nuclear electronic orbital theory, if people aren't familiar with it. So, of course, in conventional electronic structure, we have some potential that's made up of point charges at some fixed geometry at the nuclear centers, the atomic centers. And then our quantum particles are a many electron system where we have some probability density around this fixed potential. And the NEO method simply kind of moves the Born-Oppenheimer approximation so that we still have some fixed potential created by the heavy nuclei that are still treated as point charges. But the nuclei that maybe are important for creating nuclear quantum effects are treated fully quantum mechanically at the same level of theory as the electrons. So in this case, we see these two protons, these two hydrogen atoms. Now, instead of being point charges, they actually have some probability density, just like the electrons. And so we get this mixed electron nuclear wave function. And so in this framework, we can capture several important nuclear quantum effects. One of the ones that I think is important to a lot of people in the electronic structure world is the zero-point energy correction. So we capture the zero-point energy correction within just a single calculation. We also capture the delocalization of the nuclear wave function. And then we can also capture tunneling in something like a proton transfer reaction. And if we do some kind of excited state method, we can also capture vibrational excitations, all within a single unified framework. So just to make this kind of mathematically explicit, so this is the very familiar Born-Oppenheimer Hamiltonian for electrons. And we have these one-body terms of just the kinetic energy of the electrons and the attraction between the electron and the nuclear point charges, and then of course the nuclear repulsion. But the only two-body term, and the part that's hard to calculate and kind of focus of electronic structure theory, is this electron-electron two-body interaction. In the NEO method, we have all of those things. We have the kinetic energy of the electron, the electronic nuclear attraction of the classical or the fixed nuclei. And then we have the same one-body terms for the proton. I should note that when I say proton, that's because usually the most relevant nuclear quantum effects are from the lightest isotopes, and so protons. I'll say that when I really mean just like quantum nucleus, but it could be any nuclei that you want to treat quantum mechanically. So the proton or the quantum nucleus has its own kinetic energy, and then along with the electron nuclear attraction to the fixed nuclei, there's also a quantum nuclei repulsion with those. And then, of course, the same term here. But then crucially, the hard part, the two-body terms, we still have the electron-electron part, but we also have the electron-proton attraction term, which now is non-trivial. It's not a one-body term anymore. Now it's a two-body term. And then, of course, if we have multiple protons, we also have the proton-proton repulsion. So what's the simplest way we can treat this? Well, it's the same as electronic structure theory. We could treat this in the mean field with Hartree-Fock. In this case, it's NEO-Hartree-Fock. And so what Hartree-Fock theory yields is a ground state that is a Hartree product of electronic Slater determinants and protonic Slater determinants. And so these are converged self-consistently where the electron-electron interaction and also the electron-proton interaction and proton-proton interaction are treated at the mean field level and then converge self-consistently in this product form. But just like in conventional electronic structure theory, this only gives you a rough picture of this many-body interaction, and specifically the electron-proton interaction can be even more energetically important than the electron-electron repulsion because it's an attractive term. And so the electrons can get right up there on the quantum nuclei. And so it's really important to capture this electron nuclear attraction accurately. And so to do that, we need to go beyond mean field theory and specifically the electron-proton correlation, just like electron-electron correlation, is key to having an accurate method. So just to give a kind of outline of the methods I'm going to cover, I'll cover a few methods that I've done some work on, and then also just to give an overview of all of the kind of ab initio methods in Q-Chem. I'll also cover some stuff I didn't work on, specifically the multi-reference methods. Everything I have in bold here is available right now in Q-Chem 6.3. And the stuff in italics is already implemented in Q-Chem in our development version, and it's going to be merged soon as papers get submitted and stuff like that. So kind of the three main categories that I'm going to talk about are NEO coupled cluster theory. And so NEO CCSD is already in Q-Chem. And then higher order coupled cluster theory with some partial triples terms and perturbative triples. And this was originally developed by Fabian Pavasevich, and Tanner Culpet was on the original paper. And our grad student in the group, Rowan Gowdy, is currently has implemented these triples terms in Q-Chem, and it's going to be merged soon. Then the second category is lower scaling, kind of perturbative methods, and those include scaled opposite spin OOMP2 and SOS CC2, so perturbative coupled cluster. These were also devised by Fabian Pavasevich, and Benjamin Russo was on the original paper. And then I have implemented these methods in Q-Chem. And then finally, I am going to talk about some NEO multi-reference methods, NEO-MCFCF and NEO-MRCI. And these were developed by Christopher Malbon, who is a postdoc in the group, and Rachel Stein, a grad student in the group. So I'll start out by talking about NEO-coupled cluster theory. So NEO-CCSD, we can write out the exponential ensembles, like I'm sure most of us have seen in conventional coupled cluster theory. And so in NEO-CCSD, we include all the singly and doubly excited determinants in this coupled cluster expansion. But in the case of NEO-coupled cluster, for example, the T1 amplitudes, or the T1 operator, includes single excitations in the electronic space, and then also single excitations in the protonic space, or the quantum nuclear space. And similarly, for the T2 operator, we have electron-electron double excitations, or doubly excited determinants. But we also have then joint electron-proton doubly excited determinants that really are important for capturing that electron-proton correlation that I was talking about. And then again, if we have multiple quantum protons, we also have proton-proton doubly excited states. I'm not going to mention these a lot in terms of correlation because proton-proton correlation isn't super important due to their localization. But electron-proton correlation is really key in capturing the qualitative nuclear quantum effects in these methods. And so just like conventional coupled cluster with singles and doubles, this is an order n to the 6 scaling method. But in this case, the n includes both the electronic orbitals and also the protonic orbitals. So this is kind of like a few benchmarks to give us an idea of how well coupled cluster theory works in the context of NEO. So the one on the left is a simple molecule, FHF minus, where it's just two classical fluorine atoms with a quantum nucleus, a quantum hydrogen in between them, and we can plot the nuclear quantum density of this proton. And we do this in 3D, and then if we take a slice along the bonding axis, we can plot it here. So the red line here is what we get if we do Neal-Hartree-Fock. And the black line is our kind of more or less exact reference that we can do for small molecules like this. And the way we do these references for kind of benchmarking these theories is a grid-based method, the Fourier grid Hamiltonian method, where we do a bunch of single point calculations, like tens of thousands or even sometimes hundreds of thousands of single point electronic structure calculations with a conventional electronic structure method to get a grid-based potential and then solve the vibrational Schrodinger equation on that potential to get the actual vibrational wave function. And so for these small systems, that gives us something to compare to see how well nuclear electronic orbital theory is capturing the exact vibrational wave function. So we see here with the red line from Neal-Hartree-Fock theory, it's not doing very well. It's very overly localized, so it's not capturing that nuclear delocalization that we expect. And then when we do Neal-coupled cluster theory with singles and doubles, the wave function is much more delocalized, and it's approaching quantitative agreement with the exact reference. So we can also look at the energetics, and a common kind of observable that we can use to benchmark this theory is the proton affinity. So just like electron affinity, it's just the energy difference when you add the particle, in this case, adding a proton to these molecules, either anions or neutral molecules, and you protonate it and see what the energy difference is. And crucially, when we add a proton, it adds a degree of freedom, and therefore it changes the 0-point energy of the system. And so if we were to do this with conventional electronic structure theory, you'd have to then compute the Hessian of the new system and look at the 0-point energy correction after you add a new particle. But in NEO, we get this in a single point calculation because 0-point energy is included. The 0-point energy specifically of this added proton is included in the calculation. So we compare for this set of 12 molecules, the proton affinities, and compare to experiment from the literature. We see that Neal-Hartree-Fock theory is way off. It is, more than 10 kcals per mole off in terms of mean absolute error compared to experiment, which means it's not actually capturing the quantitative 0-point energy correction of this quantum hydrogen. If we do something less than CCSD, so like just a simple one-shot MP2 correction, it gets better, it gets closer, but it's still, more than 5 kcal per mole off the mean absolute error. And then if we look at NEO coupled cluster with singles and doubles, it's getting very, very close to our 1 kcal per mole kind of threshold for chemical accuracy. And in fact, there's some uncertainty in these experiments of plus or minus maybe 2 kcals per mole. So CCSD is starting to approach quantitative accuracy with experiment. And again, these are just single point energy calculations that capture the 0 point energy of this added proton. But what if we want to do better? What if we want to get really within that chemical accuracy threshold? Well, one of the big selling points of coupled cluster theory is that it's systematically improvable. You just add more terms to the cluster operators, and you can, in principle, capture more correlation energy. And so the kind of next step after coupled clusters with singles and doubles for capturing electron-proton correlation is to add triples just of the mixed electron-proton term, and specifically of the double electron excitation and single proton excitation. So we call this TEEP, the triple electron-proton excitations. And this is a triples term, so in principle, it then brings it to the same scaling as full non-perturbative coupled cluster with singles, doubles, and triples, which would be n to the 8th, where in this case, again, n includes both the electrons and the protons. But because this is only a term involving mixed excitations between electrons and protons, each of the sets of excitations, including just one type of particle, so like the electronic excitations, are still n to the 6th, because we're only treating the electron-electron correlation up to doubles. So as is often the case, we have one quantum proton and many quantum electrons. In that case, more or less, the limiting factor is the electron-electron part, which is still n to the 6th. So this is a way of capturing more quantitatively the electron-proton interaction while not blowing up the cost of the entire method. So what happens when we introduce this triples electron-electron-proton interaction? Well, we see for the proton density in FHF minus, the purple line here now is with the triples correction, and without the triples correction, just CCSD is the blue line. So we see we're getting even more quantitative accuracy, closer and closer to the grid-based reference calculation. And the same is true for the energetics. So where we're getting close to chemical accuracy and within close to the experimental error threshold for NEO-CCSD, NEO-CCSD TEEP is even lower in error and actually below the threshold for chemical accuracy. So now I'm just going to talk about so I've talked about some small benchmark systems where we can get an exact answer, or we have some experiments to compare to for these kind of single molecule observables, and it proves that this is an accurate way for capturing ground state nuclear quantum effects. Now I'm going to talk about an application of NEO-coupled cluster theory that was enabled by an efficient implementation with density fitting for coupled cluster theory as it is in Q-Chem. So in Q-Chem, we have implemented NEO-CCSD with density fitting, and it's capable of treating, a handful of molecules with a fairly large basis set. So here we studied these needed water tetramers. So these are interesting systems for kind of studying the solvation structure of an excess an excess proton in like an acidic solution. And probably some of you have heard of this, like the eigenstructure and the Zundel structure of the excess electron. So like the H3O plus versus H5O2 plus. And these are kind of the extended solvation structures when you consider 4 water molecules solvating this excess proton. So the relative energy of these isomers is very small. There are small differences in energy, and the 0-point energy of the quantum protons makes a big difference in the relative energetic ordering. So in these calculations, we treated all the electrons with AUG, CC, PV, TZ And then we treated all 9 of the protons on each of these clusters quantum mechanically at the same level of theory with coupled cluster theory with a fairly sizable protonic Gaussian basis set. So here are the results for the relative energies of these water clusters where the ring isomer has been set to the reference energy. So what we see, let's first look at what we see with just plain old conventional electronic structure theory, in this case CCSD parentheses T, which is a reference calculation that was in the literature. And what we see is that in this ordering, the Zundel ions, the Zundel isomers, are actually higher in energy than this ring isomer. However, if you do a 0-point energy correction, if you calculate the Hessian and calculate the 0-point energy, whether you're using just the normal modes or also doing an anharmonic, like the PT2 correction, you see this black line here where the Zundel ions are very clearly lower in energy than the ring isomer. And so this is an interesting example where when you do the extra work in the conventional calculation to calculate the 0-point energy correction, you actually get a qualitatively different trend in the energetic ordering of these isomers. And encouragingly, and as we would really hope and expect, NEO-CCSD captures that same trend where the 0-point energy of the protons actually lowers the relative energy of these two extended Zundel ions. So this is a nice example of where capturing the ground state 0-point energy is important for qualitatively assessing the relative energy of these structures. So I'll briefly touch on a calculation that I did for these neutral water hexamers. And again, it's a kind of a similar system in that the solvation structure, or the hydrogen bonding structure, is and the relative energy of the isomers is strongly influenced by the 0-point energy of these quantum hydrogen. This is kind of pushing the limit of what we can do, at least easily, in a day or two, with coupled cluster singles and doubles in the Q-Chem NEO implementation. And we did this with a CCPV-TZ electronic basis set, a somewhat smaller protonic basis set, but we treated all of the quantum protons, once again, quantum mechanically. And what we looked at in this study is if we look at the interaction terms, so like the pairwise interactions or the 3-body interactions, the 4-body interactions, and do a many-body expansion of these hexamers, how important are the nuclear quantum effects for each of those terms? How do they affect the pairwise interaction energy? How do they affect the 3-body interaction energy, et cetera? And we did that by looking at the interaction energy with conventional electronic structure theory, so no 0-point energy correction, and then taking the energy difference with the NEO one. And what we see is that for these isomers where there are many hydrogen bonds, so in this case, it has, I think, 9 hydrogen bonds, you see that at high order, so 4-body, 5-body, and even 6-body, the interaction terms strongly depend on nuclear quantum effects. And this is captured only at the CCSD level of theory. At the MP2 and DFT, so these are NEO-DFT and NEO-MP2, the interaction energies fall off at the 4-body level. And with coupled cluster theory, we see higher order interactions where there are more hydrogen bonds. And so this is a nice example of, one, doing some fairly sizable systems with a lot of quantum protons with our implementation in Q-Chem, and 2, seeing that actually having a higher level treatment of the correlation energy, and specifically the electron-proton correlation energy that gives us these nuclear quantum effects, can be important for these systems. So what if we want to do bigger systems, or we don't want to wait as long for our calculations? So the next part of my talk is going to be about low scaling approximations to NEO-coupled cluster theory. And these approximations rely on a second order truncation, so a perturbative truncation of the T2 operators at the same level as MP2. And so the first version is NEO-CC2, so second order coupled cluster theory, where you treat the T1 amplitudes exactly the same as you would in NEO-CCSD, but the T2 amplitudes now are truncated at the second order perturbation theory level. And so because these are the limiting factor in computational scaling, this yields an order n to the 5 method. So the same as MP2. We can go a step further, and instead of staying within the framework of coupled cluster theory, we can also do orbital optimized MP2. So this is what was introduced by Head Gordon in 2007. And in this case, the energy is still evaluated at the MP2 level of theory, but instead of doing T1 calculation to do the iterative relaxation of the orbitals, now we explicitly use this unitary operator that has these orbital rotation, these occupied virtual orbital rotations built into it. And we are actually directly optimizing the orbital coefficients with this operator and variationally optimizing the orbital coefficients until we reach a minimum in the presence of this MP2 level correlation energy. And again, this is at the level of MP2, so it's an order n to the 5 scaling method. So how well does this do? How important is this orbital optimization, either from T1 amplitudes or from a direct variational minimization of the coefficient matrix? Well, if we look at these same benchmarks, first, if we look at the FHF minus density, the proton density, what we see is that it definitely helps you localize the proton density relative to the mean field answer. So the orbital optimized MP2 and CC2 densities are certainly more delocalized than what we get from the mean field answer. But they're certainly not anywhere close to the level of delocalization we get from these high accuracy coupled cluster calculations. And when we look at the energetics, the orbital optimization really doesn't do that much. And so the truncation of the correlation energy at the second order is really leaving a lot of the electron-proton correlation kind of on the table and not really capturing enough to accurately represent the 0-point energy of this added proton. And therefore, we're not getting anywhere close to chemical accuracy with these orbital optimized methods. However, just like in conventional electronic structure theory, there are ways of using some single empirical scaling factor to maybe improve the applicability of these methods. So in electronic structure theory, there is the scaled opposite spin approximation, where you ignore the same spin correlation energy and set that to 0, and then scale with a scaling factor larger than 1, the opposite spin correlation energy. And this kind of exploits a systematic underestimation of the opposite spin interaction when you are doing a second order truncation of the correlation energy. And so in that spirit, we also recognize that there is a systematic underestimation of electron-proton correlation energy at the second order level. And therefore, we use a scaling factor for the electron-proton correlation energy. In this case, we call it SOS prime CC2 and SOS prime OOMP2, the prime being that we are also adding an additional scaling factor to the correlation energy. And this is empirically derived, but a single scaling factor for all systems. So it's not system specific, not observable specific. And for OOMP2, we use a scaling factor only slightly larger than the opposite spin. So we use a scaling factor of 1.4 and then a scaling factor of 1.6 for CC2. And then for the electronic part, we just stick to what's in the literature for the conventional electronic structure theory. So how well do we do now when we use a single scaling factor to correct the electron-proton correlation energy? First, on the left, we look at the proton density of FHF minus, and we see that we are getting much, much closer to the coupled cluster level of accuracy in the protonic density. We're getting a very delocalized protonic wave function that is approaching the level of accuracy of coupled cluster theory. And that's simply from adding a single scaling factor to the electron-proton correlation. It's even better in the case of energetics, where now this scaling factor is actually correcting the 0 point energy to be in almost quantitative agreement with coupled cluster theory and very, very close to the level of chemical accuracy. So we see errors across these 12 molecules in proton affinity of very close to 1 kcal per mole, both for scaled opposite spin SOS prime OOMP2 and SOS prime CC2. So this is a really nice result because it shows that just with one simple scaling factor, we can really correct the deficiencies of second order perturbation theory and more or less fully capture the electron proton correlation. So now I'll revisit the the application that I spoke about earlier, where we're looking at the relative energies of these protonated water tetramers. And as I pointed out before, in the conventional case, with and without a 0 point energy correction, we get qualitatively different trends in the relative energy of these different isomers. And with NEO-coupled cluster with singles and doubles, we capture the correct trend in the presence of the 0 point energy correction. And when we do NEO SOS prime OOMP2 with this scaled opposite spin and electron proton correlation correction, we get almost exact agreement with the NEO CCSD answer. And so we capture the correct trend in the relative energy of these tetramers using a much lower scaling method. And so this is a nice result as well because it gives us a kind of encouragement that we can use this method for larger systems where maybe CCSD would be really difficult, and it will probably give us a qualitatively, if not quantitatively, correct answer. So one of the larger systems that we use this method on is larger protonated water tetramers. In this case, hexamers. So in this case, it's a protonated hexamer and also protonated heptamers. So 7 water molecules with an excess proton. And with this theory, we can use a full augmented CCPV-TZ basis set for the electrons and a full-sized protonic basis set where all 13 in the case of hexamers or 15 in the case of heptamers, protons are treated quantum mechanically. And this is enabled by our implementation in Q-Chem, where again, we use RIMP2 style density fitting to avoid the full memory cost and to speed up the calculation. And so now we can compare the relative energies of these much more complex interactions in these larger water clusters. And so here is a plot of some of these, a comparison of the relative energies of some of these water isomers. And kind of the main qualitative takeaway here is that if we look at conventional electronic structure with a harmonic 0 point energy correction, that's the red line. And if we look and then we went and we did a VPT2 anharmonic correction to the 0 point energy, and we saw that there is a qualitative difference, specifically in this last energy difference here, where the prediction yielded by a harmonic theory, just doing the harmonic 0 point energy, is actually in qualitative disagreement with the anharmonic 0 point energy. And the NEO SOS prime OMP2 result actually is in close agreement with the anharmonic corrected 0 point energy in conventional electronic structure theory. So this is kind of underscoring the fact that NEO is not only capturing 0 point energy corrections at the level of a single point calculation, it's also doing so not at the level of like a normal mode analysis, but actually capturing the full anharmonic 0 point energy of the system. And qualitatively, the same trend holds here for heptamers, where if we do a harmonic analysis, the 0 point energy predicts this trend. If we do an anharmonic analysis or an anharmonic correction to those frequencies, then we get this prediction here, and NEO is in close agreement with the anharmonic correction. So that's kind of an overview of the ground state NEO methods for capturing nuclear delocalization and zero point energy in the single point ground state calculations. And in the last part of this talk, I'm going to talk a little bit about NEO for excited states. So of course, like I mentioned, uh, if we're capturing these vibrational wave functions, then in principle, we should be able to capture the vibrational or the mixed electron vibrational excitation energies. Um, and this is a very difficult task in the framework of a single electronic structure theory calculation. And that's simply because the energy scale of vibrational transitions is on the order of hundreds of wave numbers. And 1 kcal per mole, so what we would call chemical accuracy, is around 350 wave numbers. So if we're going to do a single electronic structure calculation with no Hessian or anything like that, and just resolve these states, both electronic and vibrational energies, we have to have a very high degree of precision to resolve accurately these vibrational states. Additionally, there's another complication, which is that the protonic wave function is much more delocalized and much more and has a node at the origin in the excited states. So if you remember, for the ground state protonic density, it is peaked. It might be delocalized, but it's peaked at the origin. It's peaked where the atomic center is located. But in the case of the excited states of the proton, they correspond to what we could qualitatively call bending modes, degenerate bending modes, like we'd see if we just did the normal mode analysis, and a stretching mode of the hydrogen relative to the heavy atoms. And the wave functions both have nodes at the origin. So we have essentially the complete opposite situation of conventional electronic structure theory, where 100% of the nuclear charge is located at this single point. In this case, the nuclear charge is completely delocalized away from the origin. And so this has required devising different electronic basis sets that no longer are based on the singular cusp condition for a point charge located at the atomic center. So the method that I'm going to talk about for calculating NEO-excited states is based on NEO-CI theory. So we all probably know that the CI expansion is just doing a linear expansion with respect to the set of reference determinants, generally the Hartree-Fock orbitals. So in this case, for NEO-CI, indeed, the determinants mu are Hartree products of electronic and proton orbitals derived from Neo-Hartree-Fock theory, and we can do this linear expansion and find these CI coefficients. But the version that is implemented in Q-Chem goes a step further, and it is actually a multi-reference CI implementation where the determinants, the set of determinants that are used in the CI expansion aren't limited just to the Hartree-Fock determinants. They're now re-optimized within an active space via an MCSCF, so like a CAS-SCF or RAS-SCF optimization, where this kind of static correlation multi-reference character is incorporated by doing an optimization in this active space. And by doing this CI expansion, we can then get an accurate answer for the ground state and then also resolve all of these vibrationally or vibronically excited states. So as a first example, I'm just going to show the excited states of helium H helium. So just two helium atoms with a proton in between. And this is kind of a simple test system for resolving the different vibrational modes of a small molecule. We can see if we look at the vibrational excited state density that the lowest energy vibrations or the lowest energy excitations, I should say, look like bending modes. So it's bending in the X and the Y direction. However, the next excited state isn't a stretching mode. So it's not limited to the fundamentals. Actually, the second highest energy excited state corresponds to an overtone, so a double occupation of these bending modes, where we actually have two nodes, and it's twice the energy of the bending mode. And then, of course, we also have a combination band where both of these two degenerate bending modes are simultaneously occupied by a single quantum each. And so this is notoriously difficult to capture in mean field theories of NEO. The fundamentals, maybe one can capture in NEO TD-DFT, but the overtones and combination bands that have this kind of multi-quantum character are very difficult to capture. And so if we look at, again, an FGH reference calculation, we see that the overtone and the combination band have roughly twice the energy of this lowest energy bending mode. And then the stretching mode is higher in energy than these two double occupations of the bending mode. And NEO-MRCI captures this correct physics where we have a bending mode and then two overtones and a combination band before we get to the stretching mode. So it's capturing the correct physics of these vibrational transitions, and it's also in the correct frequency range. If we look at how it's doing for the fundamental frequencies, we saw that for helium H helium, the stretch was a little bit off by a few hundred wave numbers compared to the exact reference theory. Here, looking at three different systems, we see that it is capturing the fundamental mode frequencies correctly in a variety of small molecules, both for a terminal hydrogen and an internal hydrogen, in positively charged, neutral, and negatively charged molecules. And although there's still work to be done to make it quantitatively agree, I think a lot of that comes down to limitations in basis sets. And essentially, we're capturing a high degree of the electron-proton correlation that really determines how this vibrational structure appears. So I'll quickly just talk about a non-CI and a much lower level theory that I developed to capture electronic and vibrational excited states within the NEO framework. And this is coming from the aforementioned NEO SOS prime CC2 theory that we saw with a single scaling factor works pretty well for the ground state properties. And CC2 is a really nice theory for generating excited states because unlike some of these EOM coupled cluster theories, it has a really simple derivation for the excited state Jacobian, and it retains the same scaling as the ground state method. So order n to the 5. I didn't mention before, but for the SOS implementation, in principle, can actually be lowered to order n to the 4 with density fitting because of the neglecting the same spin term. So in general, we can retain this low scaling that comes from the ground state method, but expand it into the excited state Jacobian that looks very similar to what we get from from EOM CCSD, for example, EOM CCSDT. And so we have this single singles block, this single doubles block, and this double singles block. And then by far the largest block of this excited state Jacobian is the doubles doubles block, which is kind of what's so difficult to calculate in EOM coupled cluster theory. But in CC2, this is actually diagonal and just consists of the energy denominators due to the perturbative nature, the perturbative truncation of the T2. And so because this largest block is diagonal just as a feature of the theory, it makes it really, really easy to expand it into the excited state. And so here we can compare the scaled opposite spin SOS prime CC2 results to the reference calculation and to the high level MRCI. And we see that we get this qualitative feature of the overtone and the combination band being roughly twice the bend. It's not quite as quantitatively in agreement with the reference, but we still get the correct physics. And then we also get the stretching mode. So we're kind of capturing these interesting physics with a really low scaling method. And then if we look at how it captures the fundamental vibrational frequencies, uh, it's in pretty good agreement with the reference and not doing too much worse than MRCI. And so in general, we can say that NEO SOS prime CC2 with a single scaling factor performs surprisingly well for calculating the excited states of molecules and specifically the vibrational excited states, and kind of presents an interesting alternative to TDDFT, which can actually now capture, with CC2, can capture some of these overtones and combination bands. So in the last few minutes, I'm just going to talk about an application of NEO, which I definitely could not do with NEO CC2 or any single reference NEO theory, and that is hydrogen tunneling. So hydrogen tunneling is an important phenomenon, and in order to understand the proton transfer rate in many of these proton transfer reactions, you need to know the tunneling rate. And this is within the NEO framework. Hydrogen tunneling is a multi-reference phenomenon in the protonic states. And so we can see that when we see that the ground state of this kind of tunneling system is a linear combination of these two protonic states on the donor and the acceptor. And then the first excited state is this antisymmetric linear combination of these two states. And in general, we can capture these two protonic states and look at the energy difference, and that gives us something called the tunneling splitting. And the tunneling splitting, which is simply the gap between the vibrational ground state and the first excited state of this tunneling system, is something that can be observed spectroscopically and can be used to make conclusions about the rate of hydrogen tunneling in these systems. But within NEO, it requires a multi-reference treatment of these protonic states. So I should say the previous work on the excited states was from Christopher Malbon, who implemented NEO-MRCI in Q-Chem. And now Rachel Stein, a grad student in the group, has been working on NEO-MRCI in Q-Chem and doing these multi-reference hydrogen tunneling calculations. So we can look at the tunneling splitting as a function of the donor acceptor distance for these small molecules. I should note that at each of these distances, of course, the heavy atoms are fixed. To calculate a true tunneling splitting, one needs to take into account the motion of these heavy atoms. But in general, we're kind of resolving that by taking different distances and looking at how the tunneling splitting changes as a function of donor acceptor distance. What we see now when we compare the NEO-MRCI result to the reference calculation with a grid is that we essentially get quantitative agreement, and therefore we are really, really accurately capturing this multi-reference set of states in the protonic ground state, the tunneling ground state, and first excited state, and therefore we're capturing the tunneling splitting with quantitative accuracy. And then finally, something that experimentally is of a lot of interest, if you want to know something about the mechanism of proton tunneling, doing isotopic substitution and looking at how the rate changes is a common technique for studying these proton transfer reactions. And so it's important that this theory be able to capture this isotopic substitution and get the change in rate as a function of the nuclear mass. So in this case, we're looking at this larger molecule compared to the previous ones, malonaldehyde, where again the heavy atoms are fixed at each donor acceptor distance. But what we see is that we can accurately capture the proton tunneling rate, or the proton tunneling splitting, but we can also accurately capture the tunneling splitting if we substitute deuterium. And we see that it is more than a factor of 10 lower, which is qualitatively makes sense. It's a heavier a heavier particle, and therefore it's going to be less delocalized, and its tunneling rate is going to be lower. And so the main takeaway is that we can, with a high degree of accuracy, capture the tunneling splitting of these proton transfer reactions, and we can also capture the isotopic substitution effects. So that's kind of an overview of all of the NEO wave function based methods that are implemented in Q-Chem. Again, I first talked about NEO coupled cluster with singles and doubles, and then the expansion to triples. NEO CCSD is already in Q-Chem. NEO CCSD TEP and parentheses T are coming soon, already implemented and coming soon to Q-Chem. I talked about the lower order, lower scaling approximations to coupled cluster theory, OOMP2 and CC2. OOMP2, again, is already in Q-Chem, and CC2 is already implemented and coming soon. And what I just talked about a few minutes ago, CC2 can also be used for excited states, which again is also in Q-Chem. And then finally, and the last part of my talk, I talked about NEO-MRCI and NEO-MCSCF, which can capture both the excited states of small molecules and also the multi-reference character of the tunneling proton. And both of these methods are available now in Q-Chem. So I just want to acknowledge my advisor, Sharon Hamas-Schiffer, the Hamas-Schiffer group, and specifically Christopher Malbon and Rachel Stein, who implemented and did the studies with this NEO-MRCI, Rowan Gowdy, who implemented the couple cluster triples corrections, Fabian Pavasevich, a former postdoc who devised a lot of these couple cluster and perturbation theory methods in NEO, and then Benjamin Russo, Coraline, and Tanner, who worked on this as well. So thanks for your attention, and I'm happy to take any questions.
Thank you so much. That was a phenomenal talk. If anyone has any questions for Jonathan, please go ahead and post them in either the chat or the Q&A. Okay. I don't see any questions. Here's one. How was the scaling factor in the SOS MP2 optimized?
So we optimized it so it was actually done differently for SOS MP2 and SOS CC2, but essentially it converged to the same answer. So essentially, if you fit it to the proton density, it was fit to the proton density for, I think, FHF minus and HCN for CC2. And then if you do that, it just works for the proton affinities. And I think for SOS OOMP2, it was originally fit to a small set of the proton affinities, and then tested on a larger set. So in general, either the energetics or the proton density can be used to fit the SOS scribe, and they pretty much yield the same answer that then if you test it on a larger test set, it just works.
Okay, so either one should.
Yeah, so for CC2, it was fit on the density. So if I go back to this. So it was fit on the density. Oh, I went too far. For FHF minus and I think HCN. And so then these results for the proton affinity, it wasn't fit at all for energetics. And it just worked well, even just matching the proton delocalization. And then I think the inverse was true, if I remember correctly, for the SOS prime O and P2. we fit it to a small subset of the proton affinities, maybe one like negatively charged one, neutral one, um, and then it it just works well for the entire set based on the ones that we fit it to.
Okay, that makes sense. Um, oh, and we have another question. How can you compare non-Born-Oppenheimer QM calculations with this method?
That's definitely an interesting question because the reference that we're using, the kind of grid-based reference, of course, assumes completely adiabatic separation between the vibrational wave function and then the electronic surface. Um, and so, in principle, NEO should capture the non-adiabatic character, so the non-adiabatic coupling between the quantum degrees of freedom, be they nuclear or electronic. Um, how one can compare them, I think usually for non-Born Oppenheimer QM calculations, all nuclei are treated, so heavy nuclei and light nuclei. And in that case, we do have implementations of NEO with either Ehrenfest dynamics or surface hopping dynamics. Um, but for example, tunneling splitting, we have ongoing work comparing the tunneling splittings obtained from NEO to those obtained from like ring polymer instanton theory. And in general, yeah, it's I guess I don't know specifically how what observable you're asking about comparing, but in general, yeah, it should capture non-adiabatic characteristics of the systems and extension to treating all nuclei dynamically, like with an Ehrenfest type approximation, kind of allows you to do the full real-time simulations of non-Born Oppenheimer effects.
And I remember that was recently the NEO version of the non-Ehrenfest stuff was in 6.2, 6.3, something like that.
Yeah, I mean, and also, so a lot of this stuff also is in DFT. So, like my kind of talk touched on a lot of these methods that are wave function based, but kind of the workhorse, just like in regular electronic structure, the workhorse is kind of DFT and TDDFT. And so a lot of these real-time methods, the dynamics methods, even QMMM, are incorporated with NeoDFT. And we don't have all those bells and whistles yet for a lot of these other Neo methods.
Makes sense. Does anyone else have any additional questions? I know we're coming up on time here, and I don't want to keep folks too long. But give it another second in case anyone wants to chime in. Okay. If no one else has any questions, if you have questions and think of them later, we will be posting a forum thread on the Q-Chem Talk forum for you to ask any additional questions. And a recording of this webinar will be posted on YouTube within the next couple of days. So keep an eye out for that. And big thank you again to Jonathan for your willingness to give this talk. It was very enjoyable to see all of the NEO stuff that that your group has been working on and that you've been working on as part of your postdoctoral work. And so, yeah, we're really excited to have these as a part of Q-Chem and to have you as one of our developers and to have you here to talk about your scientific work. So thank you.
Thanks so much.
All right. Have a great day, everyone. Bye.